on the computer. All right, let's do this thing. We are recording.
All right.
Hello, Mrs. Contreras. How are you today?
Pretty good, Mr. Kirk. How are you?
I'm doing good on this fine something day. What is it? Wednesday?
It
That
is
doesn't
Wednesday.
matter. Yeah, it is Wednesday. All right, let's get started. Let's not ramble too long. Share screen. Can you see?
Yep.
And I see the little red recording button. Let's not lose this. All right. Today we are going to look at the subset of the real numbers. So natural numbers, integers, even, odd, rational, irrational, and the real numbers. All of those subsets, sets that are smaller than, contain the elements of the real numbers. Along the way, we're going to do some proofs. But we'll get to that. We'll talk about the 4 different styles of proofs that students will learn this year. Ready to go?
Ready.
Let's do it. So the natural numbers. We're going to define the natural numbers, and then we're going to use the natural numbers to define the integers. Okay. And then use those to define the even and etc. So we need to be spot on with the natural numbers. What are the natural numbers?
Well, then that's the debate, right? Does it start at 0 or 1?
So I'm a fan of Wikipedia, and Wikipedia says that 0 is an integer.
0 is an integer, yes, but
yes.
A natural number.
That's what I meant. Yeah, 0 is totally an integer. 0 is a natural number according to Wikipedia, which we all know is always correct and is. I want to go ahead and say 0 is a natural number for a very specific reason that is going to come in a second, even in odd numbers. Is that cool with you?
Yeah.
All right, if anyone doesn't believe me, just pull up the Wikipedia for natural numbers. And it even says that it's a debate, but we're going to go 0. So okay. Let's roster notation. I think we have to do because we're like defining the numbers that we will then use to build the rest of them. Mm-hmm. So let's see. Oh, well, I'm going to add this, the counting numbers, right? That's one way to think about them.
Yes.
The counting numbers. But we have the notation. We have the technology. So here is the set. 0, comma 1, comma 2, comma 3, comma dot, dot, dot. All right.
And I'm putting in the Blackboard bold.
Oh, thank you for n natural numbers. Awesome.
Yeah.
Cool. Okay, so that is a subset of the real numbers. These are all real numbers. Now, what I am going to challenge you to do, and this is a little bit finicky. We're going to be a little bit loosey-goosey with this, but I want you to use the natural numbers to now define the integers.
Well, can we say that integers are the natural numbers and the negatives of the natural numbers?
Yeah. So how can we write that in a set notation? Whether that be
should do x is an element of the natural numbers.
X is an element. So
negative
okay.
X
such that x is an element of the natural numbers, and we're going to union that. Or I'm just going to say or. Is that cool?
Yeah.
Yeah. It's okay to use words in these. X is an element of the natural numbers, or
we have negative x.
Negative x is an element of the natural numbers. There we go. Boom. Sweet. All right. Those are the integers. So what would that be in roster notation? Let's write that out so we're not confusing anyone.
So we should start in the middle and we put 0 in the middle.
Mm-hmm.
We should go up to 1, down to -1, and back and forth and back and forth.
Let me get that many, and then I'll do some dot, dot, dots. Awesome. Awesome. Another way I've seen people write this is x is an element of the natural numbers, or x plus y is equal to 0, and y is an element of the natural numbers. Do you know what this is called? Like x and y in relation to variables, but in relation to each other, the fact that they add to 0.
Well, they would be opposites, right?
Opposites.
So then x would be -y.
X would be -1, y would be, so if I set y to be any natural number like 50, 47, 1, x would then be -1. They're called, let me just say this, additive inverses.
Ooh.
We're going to talk about that terminology in the next video when we talk about groups and fields. I don't know if we'll talk about fields, but when we talk about groups, we're talking about inverses. And x plus y, if they add to 0, they're additive inverses because 0 is the identity element. We'll get to this next time. All right, just throwing some big, yeah, for addition, yeah. Yeah, and then there's multiplicative inverses, and the identity for that is 1, because 1 times anything is that thing. But let's save it for next time. If we
Okay.
learned everything now, we'd have nothing to learn later. All right. Hey, why'd you put a Z?
Oh, it's Blackboard bold for Z, which is our symbol for integers.
Yeah, and
Oh, you
it's
have the cool thing for it.
Zahl, German. I think it means to count, but anyone out there that takes German or knows German, fact check me on that. If you're interested in etymology of things, write about it in your journal. But Zahl, spelt Zahlen, Zahl means to count.
Check it out on Wikipedia.
the best website ever made. So I find myself spending a lot of time on Wikipedia. All right, we have the natural numbers. Then we constructed the integers using opposites or additive inverses. Now, how can we construct the even numbers using what we have?
Well, can we say even numbers are taking our integers and then doubling them?
So 2x such that, is this what you mean? X is contained in the integers?
That's exactly what I meant.
Boom, there we go. That's a small set. Well, that's just as big as the other sets, but it's written very shortly. I don't think shortly is a word, but anyways, digress. This is the even numbers. 2x. Let's keep that one in the back of our brain because we're going to be using that in a little bit. Even numbers, 2x, such that x is a integer. Is there a Blackboard bold symbol for the even numbers?
Not that I'm aware of.
Yeah, I don't think so either. I don't think so. All right. Earlier, I said the natural numbers. I wanted to include 0. And here is why. I like plus signs more than minus signs. Can you define for us the odd numbers?
Well, can we say that odd numbers are taking our even numbers
Okay.
and then adding 1 to it?
Boom.
So we get 2x, yep, plus
Yeah.
1, such
And
that x is an integer.
Boom. And if we had, actually, this might have been totally fine, but if we didn't include 0, we're using the integers. Never mind. This doesn't really matter. I like that plus 1 though. We could make a minus 1.
But I think that having 0 in our natural numbers made our definition for integers cleaner.
That's true, and thus made our definition for even and odd cleaner. You know, the reason why I was building up to this is because in the past, we didn't define the negative numbers to be even and odd. How do you feel about that? In the past, we defined the even numbers and the odd numbers using the natural numbers, which is why I really wanted 0, so that 1 would be odd. Right here, 0 plus 1 is 1. If I didn't include 0, then 1 wouldn't be odd. 3 would be the first odd number. How do you feel about even and odd numbers being negative and positive? Is that cool? What do you think Wikipedia says?
I have no idea what Wikipedia says, but in my brain, even and odd is okay to be negative because when we're thinking about like even and odd functions, like the symmetry that we can get, like, I don't know.
True. Anyways, yeah. Yeah, people are probably getting real frustrated that I'm trying to say that even numbers are only positive. I hope so. Anyways, there you go. Even and odd numbers. That was really easily defined. Right? We're taking the natural numbers, the counting numbers, and then we are constructing these other sets. Just another quick aside before we move on. We defined the natural numbers, and then we defined the rest of the sets using the natural numbers. How would you define the natural numbers?
The counting numbers?
Yeah. So I asked, that's a loaded question. There is a way, and it's really weird, and I encourage everyone to look it up. I'll put in the description of the video what it's called. I don't know it off the top of my head, but it involves the empty set, and it's bonkers. Let's keep going.
Wow.
Natural numbers, integers, even numbers, odd numbers. Okay. We're going to use these subsets of the reals to do a few things, and then we'll get to the rational and the real numbers. Before we do that, styles of proof. So this lesson's all about the subsets of the reals, but we're going to use those things to do what we do in math, prove facts to be true. Mrs. Contreras, do you know the 4 styles of proof that we'll be looking at this year?
I think so.
Okay.
But I might need help. So
okay.
I think the first one is direct proof, where you're saying P implies Q. we're showing that.
And I'm going to add that here. P implies Q. So we're given a statement and we just like by definition show that it satisfies Q.
Can we make the arrow the right kind of arrow?
What's the right kind of arrow? Is it
The double bar.
double bar like that?
Mhm.
Okay, sweet. I got you.
Because
Cool.
otherwise it looks like P approaches Q.
Oh, true. Which we've seen already. Okay.
Yep.
Yeah.
And then there's proof by contradiction.
I'm gonna put that in number 3 just because I know the order of things in this lesson. We're gonna use proof by contradiction. Anyone who's watched like number file or anything, contradiction has probably seen some use of proof by contradiction. Okay.
Proof contrapositive.
Proof by contrapositive. We're gonna use that one before contradiction. Proof by contrapositive. What is that one?
That one's not Q implies not P.
Not Q implies not, oops, that's not a Q. This is a Q. Wait, so talk this one out for me. If I have a statement, an if then statement, P then Q, what does this not Q then not P mean?
So like we wear Blairwear on Fridays, right?
Okay.
The staff wears Blairwear on Fridays. So if it's Friday, then the teachers are wearing Blairwear.
Let me write this. If Friday, then teachers wear Blairwear. Okay.
So then proof by contrapositive would be saying if teachers aren't wearing Blairwear, then it's not Friday.
Boom. Which these two statements are logically equivalent, right?
Mm-hmm.
If one is true, then the other must be true. So proof cut by contrapositive, I think, is saying proving Q imply Q. That's like Q and P combined. Trying to prove P implies Q can be difficult, but it might be easier to say not Q than not P, which will prove the thing that we wanted to prove. If that's kind of not making sense right now, we're going to use it in a second, and I think it'll make a little bit more sense. We're going to do these 3 in this video, but number 4 we're not going to do. Do you remember what the 4th one is?
Is that proof by induction?
Yes, proof by mathematical induction.
And if you're excited about that, then that's the one where you have the base case, and then you have the induction case, and then
It's like dominoes.
induct it.
You knock one domino down and it knocks them all down. That analogy makes no sense for people that haven't seen it before, but that's going to come later. Way later. The first 3 we're going to tackle today. All right, so let's use the first one, direct proof. Mrs. Contreras, I want you to help me prove that the sum of any 2 even numbers is even.
Okay. So if we're going directly, that means that we're assuming that we have 2 even numbers, and we just need to show that their sum is also even.
So we have a definition of even, right?
Mm-hmm.
We've defined it today. What was it again?
That when we have an integer, our even numbers are double that integer.
Okay. So 2x such that x is a natural number, is an integer. Okay.
Mm-hmm.
So big thing in direct proof and all proofs in general is when you start, you need to define everything that you're going to use. So the sum of any 2 numbers is even. That's what we're trying to prove. Let's bring into existence some even numbers. So let's go with A and B.
Okay.
What were you going to say?
M and N, but
Yeah. Well, we can use M and N. We're about to get to it. Let A and B be even numbers. I'm a stickler for this. You cannot write a proof unless you define the things you begin to use. If you just start like doing crazy like math and you never told me what A and B are, then I'm lost. I think a good rule of thumb is, could you have a conversation with someone who has never done this before, maybe like a 6th grader that you're tutoring? Would they be able to follow your logic? And if you don't define to me what A and B are, then the 6th grader is going to be lost. So let A and B be even numbers. What does that mean about A and B?
That A and B can both be defined as 2 times some integer.
Therefore, All right, and we want to use words like therefore, thus, then. You don't have to be so fancy with like thus, but you want to preface the sentence with something that is bringing from the previous sentence. So let A and B be even numbers. Because of that, therefore, A is equal to 2 times M, and B is and B is equal to 2 times N. Period.
Such that M and N are integers.
There it is. All right. I said M and N, and I did not define what they were. That's a big red flag. That's what we're looking for in a good proof. Is everything clear and defined? So M and N, so B is equal to N, such that I'm going to use that symbol ST. Have we used it before?
I don't remember, but
Yeah,
it's just such a part of my life.
let me go ahead, just so people that are looking back at this later, such that M and N are contained in the integers. Sweet. Right. Nothing here has not been defined. Okay. What's next?
Well, we can add them together. So we can have A plus B equals 2M plus 2N. But then we have 2 that we can factor out, which is really nice.
I do want to add one thing. So some literature that I'm going to have you share with the students says that you should never begin a sentence with just symbols. You should always start a sentence with some words. So what can we put in front of A plus B?
Hence.
Hence, I'm cool with that. We want it to be readable. And by beginning a sentence with words, it kind of gets the mind rolling in this reading feeling. So hence, A plus B is equal to 2M plus 2N. That's just by substitution. You don't need to necessarily say that. Okay. And then did you say what to do next?
Well, we have a GCF. We have that 2 that we can pull out of both of those terms. So we can have 2 times M plus N. Yep, inside parentheses. And then we know that M plus N, since those are both integers, integers add up to other integers.
Boom. You cool with my sentence? Do I need to add anything?
That looks great.
Cool. We know that M and N are integers, so M plus N is contained in the integers. I'm going to use a new symbol in the next sentence, which I think people can use. But we know that that this is an integer. So how can we finish this?
Therefore, the sum of any 2 even integers, 2 even numbers is even.
Therefore, A plus B is a integer times 2 and is by definition even. You cool with that?
Sounds great.
Cool. All right. How do we finish every proof?
The little box.
Little box. This is the least of the pretentious ways to finish a proof. You could also do you know the other one?
That's like QED.
Yeah, QED.
So,
it feels so pretentious, doesn't it?
yeah.
My way of I just accidentally erased. No, there we go. My way of like saying QED is lame and it's pretentious is to say make up an acronym. And here's my acronym. Make up a different acronym.
I did it.
That's precisely correct. So, you know, if someone says you should write QED at the end, say, no, I did it. QED stands for like quad erect demonstratum. It's Latin. It just feels like too much. All right, boom. That's a direct proof. We started with the premise. We got to the conclusion. And we just went straight there. All right. The second proof here, I want us to use proof by contrapositive. So let's prove this. We will, and I'm even going to preface the proof with that sentence. We will prove using proof by contrapositive. But before we begin, let's dissect what this proof is even asking.
So this is saying if 2 divides n squared, then 2 divides n. Meaning that if we have n squared and it's essentially saying it's even,
Mm-hmm.
then n is also even.
Yeah. You could always feel free, everyone, if you want to rewrite this. If n squared is even, then n is even. There are other ways to prove this, but I want to showcase contrapositive. Right? 2 divides n squared. So 2 divides 5, 2 divides a million and 1. 2 divides odd numbers, but this is saying divides it into an integer. You were correct in saying, just to make sure everyone, 2 divides n squared into an integer. Okay. So what would proof by contrapositive be here?
That if n is not even, then n squared is also not even.
We want to show that if 2 does not divide n, then 2 does not divide n squared. This is a little bit easier to show, in my opinion. Okay. We want to show that if 2 does not divide n, then 2 does not divide n squared. If 2 does not divide n, what's true? If 2 does not divide n, you said before that if 2 divides n, it's even. If 2 does not divide n, what's true about n?
It's not even.
Which means it's
Odd.
boom. Since 2 does not divide n, then 2 is, I'm going to even say it, is not even.
Then n,
What?
you have 2. 2 can't not be.
Then, yeah, you're right. You're right.
n.
Right. If, then n is not even. Therefore, n is equal to 2, give me a letter.
K.
Okay, 2k plus 1. That was our definition of odd. But before I proceed, what is k?
K is an integer.
Yeah, let's just make sure so no one's like, what the heck is k? That happened to me in class the other day. We were talking about like 2 pi k, and someone came to me at lunch and was like, what's k? I realized I didn't define what k was. You got to define what k is. It is an integer. Okay. Hey, what's n?
Square?
Yeah, let's square it. Let's square n because we need to inspect n squared and see if it's not divisible by 2. Because that's our goal, to show that 2 does not divide n squared too. Let's square. Another thing people do in proofs is they don't use I, me. They don't use possessive nouns. They use more collective nouns. Let's square together n. N squared is equal to, I'm starting this sentence with a symbol, forgive me, 2k plus 1 square. 4k squared plus 1, right?
No, that's the freshman stream. Plus, what is that, 4k?
Oh, 4, I did, you know what? I did that in class today too. I wrote 2k and everyone was confused. You know, small mistakes like that can really be detrimental. All right. Shout out to my 7th period calculus class. All right, let's square n. N squared, I'm gonna make this a comma so I never started a sentence with a symbol. Let's square n. N squared is equal to 2k plus 1 is equal to 4k squared plus 4k plus 1.
Do we have secretly an odd number in there?
I think we do. Can we write it as 2 times an integer plus 1?
I think so, because we can factor out a 2 from 4k squared plus 4k. So we end up with 2 times 2k squared plus 2k. And then close those parentheses and get a plus 1. So now we have 2 times this thing which we know is an integer, because when you square an integer, you still have an integer, and when you multiply an integer by something, you still have an integer, and then you add that to another thing that you know is an integer because of multiplication, and integer plus integer is still integer, so everything in that parentheses is an integer. So we got double an integer plus 1, which is odd.
So n squared is odd. Therefore, I'm actually going to throw in a symbol. I don't know if I did it earlier. I said I was going to, but I didn't.
I think you did. It's right there.
Oh, I did use it. Sweet. Yep, it's right here. All right. Therefore, that's the symbol for therefore, 3 little dots in a triangular position. Therefore, what do we need to say? N squared, or 2, does not divide n squared. Okay.
So then we've shown by contrapositive
By contrapositive,
that if n squared is even, then n is even.
2 does not divide n implies 2 does not divide n squared. So 2 dividing n squared implies 2 does not divide n. Boom.
2 divides n.
Yeah. So if 2 divides a square, then 2 might divide the number that was squared. But proof by contrapositive, we showed that not Q, we can get to not P. That means that P does in fact imply Q. Very well done. Very nice proof. I think this is the most perfectly done I've ever done this proof. I'm usually like, it's usually way more messy than this. Thank you very much. This is one to save and post. All right. Can we continue?
Yeah.
Zoop. All right. The rational numbers. How can we define these things using the things that we've already defined?
I think rational just means that we're looking at a ratio. And so we can look at an integer divided by integer, and then we'll have all the rational numbers.
So let's go with like m divided by n.
Yep.
Such that m and n are integers. All right, so -1/4, -47/5, +100/7. How do you feel about like 100 halves?
That's fine.
That's fine. Okay. Okay. There's or how about like, I don't know, 4/6.
That's
Okay.
also fine.
Sweet.
Am I supposed to be more upset that they're not?
No,
simplified?
no, but something's gonna come up later, and we'll remember that I asked those questions. All right, so those are the rational numbers. Given 2 integers, put them in ratio. That thing is a rational number. Right. Show to me that every terminating decimal is in fact the ratio between 2 integers.
Can we just multiply by like 10,000?
Yeah. So what would it be? This is equal to 3, 4, 1, 2, 7, 5. Let me actually show what you said. You're saying multiply by 10,000 over 10,000, which is 3, 4, 1, 2, 7, 5 over 1, 0, 0, 0, 0. Boom. Right. Any terminating decimal you can rewrite as a rational number, and we could potentially simplify this, right?
Yeah, I guess they're both divisible at least by 5.
Hey,
Go from there.
Is any? Let me say this right. Is the sum of 2 rationals rational?
The sum of 2 rationals rational. Yes.
Yeah, right. Like I think we could like do a quick math problem. M plus n plus a over b. What would that be?
MB plus AN. I'm so sad that you didn't set it up so it was MBHS. That's okay.
And wait, what would it need to be?
M over H. No.
And then b needs to be in the denominator.
Yeah. And then
MBHS. So MB plus HS over HB.
HB. Yep.
Nice. Yeah, the sum. So you could also break this up into 34 plus 1/10 plus 2 100ths plus 7 1,000ths, right? Plus 5 10,000ths. Well, which will simplify this. Right? Any terminating decimal is rational. More complicated question. Any repeating decimal, 5.34, 7.2, 146, 146, 146, 146, triple lit to my music people out there. Any repeating number is apparently rational according to this piece of paper.
which is as legit as Wikipedia.
Wait, how can we show this?
Well, can we do the strategy that we had up over there where we multiply by something to get rid of something? But
So
then,
if I multiply by, like you multiply by 10,000 to move that decimal over. If I multiply by 100, I'll move the decimal over, but we didn't get rid of the decimal though.
that's true.
Wait, so like 100 of the number is 534.34. We didn't get rid of the decimal.
Can we say that that plus 34 repeat 0.34 repeated stuff is some number?
Okay. And then 100 of that number is 534.34 repeating, right? Okay.
Oh, so now we have a system of equations, don't we? So two things. That
Okay,
are true.
wait,
So,
okay. How can we get rid of this repeating part?
well, what's 100x minus x?
99x, right?
Okay.
Equation
And then
subtraction. If we
500.
subtract these,
Mm-hmm.
those go away, right?
I think so.
529?
534 minus 5. Yep. 529.
0.000000. The threes will cancel the fours and then everything repeating after. We just got rid of it. And I think x 5.34 repeating is, what would it be? 529 divided by 99?
That sounds good.
Oh, wait, can we check that that is actually, is this the number?
Pull out the calculator.
Hey Siri, what is
I got it.
529 divided by 990? Oh my gosh, you got it.
Here's what I found.
It picked up the, oh my gosh, you got it. And then it had no idea what I wanted. So 529 divided by 9 is exactly what we wanted. How do we do that with B here?
Maybe we need to do a little bit more multiplying because our repeating section for our decimal is
It's in like a different
a little
spot.
longer.
Let's call it X though. We need to get rid of the 146 repeating.
Okay.
Can we get two numbers where the 146 repeating is in like the same column?
Like multiply.
Yeah. Like I'm rewriting it on the side over here on the previous one. We kind of lined up the other two numbers and then the 0.34 cancel with the 0.34. Can we get two numbers where it's the 146 is in the same, whatever it's called. I teach math. I should know the terminology
Decimal
for
place.
the decimal place. Yes. What two
I think
numbers?
so.
Okay.
So if you have 10x, then we have that is 72.146 repeated.
Okay.
And then if we have that times another 1,000.
I think we need
that's
10,000, right?
10,000. Okay.
So 10, 100, 1,000. So 10, 100, 1,000, 10,000. 10,000x. That's going to be 72,146.146 repeating. And we can use the trick, right?
Yeah, the subtraction from our system of equations that we constructed.
All right, the 146s go away. And then now we have to do 72,146 minus 72. What the heck is that?
It ends in a 4.
Ends in a 4.
It has a 7.
Okay.
0.
Okay.
2, 7.
7, 2. Yeah, 2, 7.
Yeah.
Boom.
Got it.
X is equal to 72074 divided by 9990. Money. There we have it.
That would be a lot.
Sorry.
That would be a lot of money.
Is it a lot of money?
Yeah, $7.
$7? Yeah, you can do it $7. You can go to Subway. Eat fresh. I don't know if
This is
Subway's
not
fresh.
sponsored by Subway.
But if you want it to be sponsored by Subway, if you're out there, if you're watching. All right. we just showed, I think that we didn't really do it, but we kind of just showed something major, right? What did we just show?
Any terminating or non-terminating, but still repeating decimal. Wait.
And terminating is like repeating, right?
Yeah, I guess so.
Right? What would this be as a repeating decimal?
Repeating zeros.
Yeah, like 34.12750 repeating. Right. So I think we just showed that any repeating decimal is rational.
Excellent.
What is the contrapositive of this?
Any irrational is a non-repeating decimal.
Any irrational number.
I unintentionally wore the perfect shirt for this. Are you ready for my shirt?
I'm ready.
It's
Let
my
me stop
favorite
the share.
irrational
Let me
number.
stop the share.
This is it's a pineapple.
Pineapple. Oh my god. Woo.
All right. Anyway.
All right, let me go back. Come on. There we go. Any irrational number is non-repeating. That's a pretty powerful statement. That's how we know that pi is irrational, because it's non-repeating. Non-repeating is non-repeating. If a number is repeating, then it is rational. And the contrapositive says if a number is irrational, then it is non-repeating. So I think that's how we can define the irrational numbers. Any number that is non-repeating or has a non-repeating, what would it be, decimal? What?
Mantissa.
Mantissa, what's that?
It's the stuff after the decimal.
Whoa, not right. How do you spell that?
I'm going to try to write it. Mantissa, I think.
Oh, I was off by an S if you are correct. Boom. All right. So with that said, we have now defined the natural numbers, the integers, the even numbers, the odd numbers, the rational numbers, the irrational numbers. What are the real numbers going to be?
The union of the irrationals and the rationals.
There we go. The real numbers are the set of numbers such that x is rational or x is irrational. Well, I don't want to say not rational. X is irrational. Do we have a set symbol for the irrational numbers? I don't think so.
I think it's reals minus rationals.
True. I sometimes say cube prime, but that's probably not right.
Okay.
But just to like have self-referential in class, whatever.
Sure.
Reals minus, yeah. Boom. Basically, the irrational numbers are everything in between the rational numbers, but one way to think about it is the non-repeating stuff. Because if it's repeating, it's rational. Boom. All right, we have the real numbers, we have the irrational numbers, we have everything else. One last proof and then we're out of here. Which one have we not done that I said we were gonna do?
Proof by contradiction, which is, so we assume that root 2 is rational, and then we show that we broke math.
We will prove by contradiction, which means let's assume the opposite and show that it breaks math, to reiterate what you said. So let root 2 be rational.
So that means that there has to be a m over n that can represent root 2.
Therefore, the square root of 2 is equal to m over n,
such that m and n are integers.
Such that m and n are integers. I'm going to add a little caveat here. M and N can be reduced, correct? And if they cannot be, like, do you understand what I'm saying?
Mhm.
Can you help me like articulate this to the viewer?
So we want to make it clear that M over N is like fully simplified. That it's not saying like necessarily that we have an infinite number of ways of defining the exact same number. Because you can have an infinite number of ways of defining the same number just by multiplying by different ones, like something over something.
M and N is in simplest form. And if it's not, we can put it in simplest form, and then now it is in simplest form. There is a simplest form. Right? All ratios have a simplest form.
I'm not sure if we spelled simplest correctly, but that's okay.
I've totally spelled it incorrectly. Wait, can we spell it right? What would it be?
SIMPLE.
That feels wrong. I do not like that. I
This
do not
P.
like that, Sam. I am. Oh my God. Are you looking it up?
Yep.
Be quick though, because this video is getting long. Sorry, everyone. All right, but while we look this up,
SIMPLEST. There's no I.
oh, that is comfortable. Right. M and M can be simplified. Simplest. And that's going to play a role in our contradiction. All right. Square root of 2 is rational. This breaks math somehow. All right. We need to find this brokenness. I don't like the square root of 2, but I do like 2. I know a lot about 2, especially from this video with even and odd numbers. Can we square both sides?
Absolutely. So then we end up with 2 equals M squared over N squared.
Squaring both sides. 2 is equal to M squared over N squared. Ooh, I see something in our future.
Well, so then we have M squared over 2 equals N squared, right?
All right, why would you think to multiply by N squared? What do you see?
Well, the thing that we had before about having if an integer is squared and it's divisible by, if 2 divides N squared, then 2 divides N.
Mm-hmm.
So then we have a gateway into showing that we've broken math with this assumption.
Okay. So 2 divides M squared, I think is what we're saying here, right?
Mm-hmm.
Yeah. 2 divides M squared by previous proof. It's almost as if we strategically chose that previous proof to set us up to understand this proof better, right? M squared is even, therefore I just said it, dang it. I'm sorry, I took that from you. What did we prove before? 2 divides M squared?
Then 2 divides M, so then M is even.
I'm actually going to put that in between this previous proof part. Sorry to those taking Cornell notes. 2 divides M squared implies 2 divides M by previous proof. Okay. What does that say about M?
M is even?
M is even. Therefore, M is even and M is equal to 2 times K?
Sure.
For some K? Yeah. Awesome. Okay. Right. M is even. Remember how I said that M and N is in simplest form?
Mm-hmm.
What is a classic example of a number not in simplest form? Like an even divided by a
2.
Like 2 even numbers are definitely not in simplest form. They share a common factor of 2. We've just shown that M is even. If we can show that N is even, this is not in simplest form. How can we show that N is even?
Can we say that n is equal to m squared over 2?
Well, we have this up here from before. 2n squared is equal to m squared. But what do we know about m?
M is even, so m squared is also even.
By substitution, 2n squared is equal to 2k squared.
Mm-hmm.
M is
And you just
even.
multiply out, then what do
Okay.
you get? 4k squared?
2n squared is equal to 4k squared.
Which is if you divide both sides by 2, then you get n squared equals 2k squared, which means that 2 divides n squared, thus 2 divides n. So now we have even and even for both m and n.
And n is also even, and n is equal to 2 times L, where L is an integer.
Sure.
Okay.
So now we can rewrite m over n as 2k over 2L. And we have a GCF in our numerator and denominator. So we don't have simplest form.
We're not in simplest form. We can reduce it. And here's the real contradiction. Are numbers infinitely reducible?
I don't think so.
Right? That's what we were saying earlier. Like, if a number is in ratio, it can be simplified to a simplest form.
Mm-hmm.
So m over n can be rewritten as k over L for some 2 separate numbers, k and L. But I think we just showed that root 2 is equal to, therefore, root 2 is equal to k over L. What can we do again?
Do it all over again.
And 2 is equal to k over L dot, dot, dot. We have a contradiction. M over n is not in simplest form and can be infinitely reduced. Therefore, what's the final sentence here?
Root 2 is irrational.
Root 2 is not a rational number. B, G, T, D. Boom. Goes the dynamite. All right, and this is I think the first lesson that ended right at the last sheet of paper. Look at that. All right, let's close this one out.
Sounds good. We didn't put our name on things.
We're doing it now.
Nice. Boom goes the dynamite.
Dynamite. Did I spell it right with like weird choices of lower and uppercase letters?
Yeah, sounds good.
Boom. Goes the dynamite. I don't know why I keep saying boom. Ready?
Ready.
Wait, we gotta do that again.
Oh.
Wait, did I stopped the share?
Yeah.
All right, here we go.